For having us here. I'm Emanuele Naccini, Technical Development Engineer from Reid. And together with me there is Sam Adshead. If you want to introduce yourself.
So I work for Home Solutions, but I've recently moved on to Zero Tech.
So we represent together, we're presenting a proposal for a new test methodology for reinforcement mechanical connections, in particular for impact loading at freezing temperatures. So we're here with invited by the Auckland Structural Group, and so we'll start the presentation and we'll kind of do it together.
It's great to see such a big crowd as well. So.
Okie dokie. So quickly, we'll introduce the topic, which is mechanical connections for reinforcement, and the requirements that we have in New Zealand for brittle fracture resistance. And then we'll introduce our proposal for this new test procedure, and which will detail for how you assemble the samples and the configuration for the test, and the temperature of the test samples and the strain rate required, and the acceptance criteria. And of course, at the end, we'll have the conclusions. So for mechanical connections for reinforcement, we have, of course, different scenarios available, like classic mechanical couplers, where the two bars are connected directly through the mean of a mechanical coupler, of course. But we also lump into this category the hybrid systems, like the grout sleeves, where there is a mechanical connection, and the other one is a grouted connection. The bars could be either with a coarse thread that works with like a continuous thread, where the deformation works like a continuous thread, or there could be a metric thread that is applied at the end of the bar with rolling or cold forging and cutting different systems. Also tapered thread, and also no thread at all, but there are some coupler systems particularly used for existing scenarios where there are existing bars that need to be extended, where there is a coupler with a shear bolts that bite into the bar. And the requirements for brittle fracture resistance in New Zealand, they, of course, come from the mechanical connections that need to satisfy requirements for, come from 3101. And from 3101, we know that mechanical connection need to satisfy the requirements for mechanical anchors, which in turn are required to be proven to have an appropriate through an appropriate test method to possess resistance to brittle fracture. And this is not just for the coupler, but this is extended also to the processed bar ends. And also there is a requirement for anchors and couplers not to be manufactured with from cast iron. So the first comment is that appropriate test method is quite generic if there is no indication of what is the test method. And unfortunately, there is no test method given either in the 3101 or in the commentary section of 3101. And the other thing is that the comment about cast iron is a prescriptive requirement, which is kind of not really what the modern standards do. Generally, everything is based on performance requirements. So with this, we look at the other standards available, like the NZTA Bridge Manual. In this case, of course, in generally what happens with the Bridge Manual is that it tries to follow 3101 where possible, but sometimes it extends the requirement, makes more adds something extra, let's say, in terms of requirement. In this case, we have some indication for how to test for brittle fracture resistance. However, this is a requirement that is specific on the material of the coupler itself. So the indication is to perform a Charpy V-notch impact test on a little sample that needs to be cut out from the coupler. So the Charpy V-notch test generally, it's a 10 by 10 by 55 mil sample that it cut out from the coupler, then it's frozen at 0 degrees and put in the Charpy pendulum, and the energy that is absorbed by the sample, of course, gives an indication of how the material is ductile and resilient. So if the pendulum swings up high and there is a brittle failure, there is little energy absorbed, so we know that it's not a good material. In this case, 27 joule is the threshold. But as I said before, this is a little sample that is cut out from the coupler. It's not checking the brittle fracture resistance of the connection. So that's the issue that we have. And it's also not what about the bar ends. This is just a coupler. So having said that, we've looked at other international standards, which are also cited by 3101 and the Bridge Manual. The first one is ISO 15835, which is a specific standard for reinforcement couplers, and is cited by both, by the Bridge Manual and 3101. And also ISO 15698, which is a standard specific for headed anchors of reinforcement, which is only cited by the Bridge Manual, not by 3101. But both of them have no requirement or comment about brittle fracture resistance and test methods for that. It almost looks like it's not an issue. So with this landscape comes our proposal. And so the idea is to perform tests on full assemblies, not just on the parts, and also to perform the test in conditions that might be experienced through the service life of the structure. And so with the low temperature that could be experienced in cold winter days, and high strain rate like we have on a severe earthquake. So, you wanna?
Sure. Yep. So obviously we're trying to identify any weakness of the connection itself. So like Emanuele said, like you can't do a Charpy V-notch on a thread, right? So, and we know that threads are often the parts that get the most work during cold forming, you know, of the end of a bar. So the need for this test is, well, I mean, it's probably debatable, and we'll get to that. But if you're going to do it, then you have to do it on a whole specimen. So we take the specimen length from the ISO standard, basically. It's pretty well established, and it's a good starting point, right? Maybe it's not perfect, and maybe we'll learn things in the future, but this test method is meant to be, here's a line in the sand, what do people think? Let's start using it and improve it over time, potentially. Basically, we have to allow a small development length outside the splice. That's pretty clear for stresses to, I guess, go back to what they would be in the parent bar. And then we need to allow some length to grip it in a normal test machine. And we probably don't want that length too long, and I'll come to that in a little bit, because we're trying to achieve a certain strain in a certain amount of time. What's this requirement? 400?
Yeah, that's for they use it for the tensile test in general, but then this is quite long, so it's 400 mil on top of what's called the mechanical splice length. So we challenged that, and we said, okay, let's go with the length that is required for the slip test, which is shorter, because as Sam mentioned before, we need to reduce this length to make our life easier for the life of the machine that will do this test, because we need to have a machine that is very strong and very fast. So to perform a strain rate that we'll discuss later, we need to shorten as much as possible. So this is the kind of good compromise, I would say. Yeah.
And you have to forgive me because I haven't looked at these slides in a little while. So we're going for 125 outside of the development, either side of the splice, and tolerance. Yeah, and some tolerance, right? Yep. The temperature. So Emanuele did a bunch of research, got in touch with NIWA, And obviously, we're looking at trying to find what is a reasonably cold temperature, realising that the probability of cold and earthquake striking at the same time is, that's what we're looking at. But got in touch with NIWA, got all the data from the coldest parts of the country, and turns out it's a very small part of the country that is cold. But, our thinking was also, we suspect that most systems won't have a problem with this, so let's start here. And if it starts being a problem, we can always relax those requirements or undertake a rational analysis of the actual risk rather than taking worst case, and combining them.
Yeah, because the map from NIWA, the one that is on 3404 is what they call it load mat. So it's the lowest one day mean ambient temperature. So it means that the temperature that you see on the map is actually over 24 hours. Mm-hmm. So the concern from Des was that is that enough? It could have a much lower temperature through the night or whatever. So that's why we got in touch with NIWA, and we have asked a couple of questions. The first one is, what is the lowest temperature recorded in New Zealand over the past 50 years, which is a whopping minus 21.6 in central Otago. And then the other question is, can you average that over 5 hours? Because it might be a trough, and so we want to be sure that it's cold, that cold for enough time for the cold to penetrate inside the concrete structure and freeze the coupler. And so for that particular station, they didn't have hourly recording, but another one close by, they had hourly recordings, and the minimum was minus 21 anyway. So and the average was minus 19.5 in these 4 hours, so we got the winner, Tara Hills. And so the beauty is that actually the data is accessible, so you can register with NIWA and download the Excel file of the recordings. And that's what we've done. So we run a bunch of analysis on the data. And so they had daily recordings starting from 1985 onwards. At that time, it was like 13,000 plus days of recording. And so we could work out the average standard deviation, the fifth and the 1%. And then we compared that with so we wanted to check, is that a normal distribution? What are we looking at? So the yellow curve that you see is the normal distribution coming from the original data, which is the blue curve with the recordings. And the yellow is the normal distribution starting from the average and the standard deviation of the original data. So it kind of resembles decently a normal distribution. The only thing is that for temperatures below minus 4, the yellow curve is a little bit higher, so there is a higher probability density for the normal the theoretical normal distribution. So you can end up with what have I done? Yeah. So the fifth and the 1% are a little bit lower. So, but we have the ballpark. So we decided, okay, let's go with minus 10. And again, given plus minus a couple of degrees for tolerance. Yeah.
Yeah. What
oh, yeah. The other thing is for the strain rate. So we covered the temperature. Now we look at the strain rate. Yes, yeah. For the strain rate, we started with the. So the first thing is that first consideration is which one is the worst case scenario for the strain rate, which is when I have a high strain rate. So the faster I go, the worse it is. And therefore, because we are implying that the strain rate comes from earthquake, so that comes from a stiff structure to have a high strain rate. So we started with, worst case scenario should be when I have a stiff structure which is not too high, so a low-rise concrete wall structure. Let's say something that has a fundamental period around 0.4 seconds, 2.5 hertz, which is quite fast, but that's a full cycle. So we want to develop the ultimate strain only in the first quarter, so not the full cycle. So we want to develop this epsilon u that we have in mind in a quarter of T1, so 0.1 seconds. So that's the first thing that we have. And then we look at the material strain limits for the, because we want to understand, so we know the time, but we have still to determine what's the epsilon u. For that one, we looked at the, of course, 3101 and the nominal plastic hinge curve at first yield of reinforcement. And then we know that the limiting material strain is the phi y times the factor kd, which is dependent on the ductility of the structure. So the more ductile structure, the higher the kd. In this case, we started with the hypothesis that we had a very stiff structure, reinforced concrete wall, chubby, so we're not expecting a huge KD. So something like 6 is consistent with the initial hypothesis, like a doubly reinforced wall of limited ductility. And therefore, the epsilon u with this, in this scenario is around 1%-ish. I'd like to point out that if we started with a more ductile structure, of course, epsilon u would be double, like 2%. But at the same time, also the time would be longer. So in the end, the fact is that I end up with the same result. So for the moment, we have epsilon u with this consideration as a target strain. We had the T1 quarter is 0.1. Therefore, the strain rate would be 0.1 seconds to the power minus 1. So if we flip the hypothesis, having a more ductile structure, epsilon u would be higher, would be 0.02. But also T1 over 4 would be 0.2 instead of 0.1. So it's kind of the same number. So we got it, and therefore that's a consideration. We want to do this one?
Sure, yeah. What is the likelihood of these two things occurring in the same time? There's a question that needs to be answered in the future probably, but if we combine them in the most conservative way, this is what we've chosen to do at the moment. And so it's like, you know, we've built a hospital in Ophir, and it's a really stiff, squat hospital or something. And so, but I guess the question still needs to be answered. Is there a problem with low temperature and high strain rate? So that's what we propose to do.
Yeah. So if we look at the probability of these two events happening together, so when we look at the high strain rate that we are dealing with is the ULS scenario. So the probability of exceedance of 1/500 in a year. And for the temperature, in that spot in the center of the South Island, at the bottom of the South Island, where, you know, which is the coldest spot in New Zealand, we know that a temperature less than -10 is only recorded for 2 or maybe 3 days a year. So for that location, you have that event happening with an earthquake, which is a ULS earthquake, at the same time, and an earthquake only lasts for a couple of minutes, so that's very unlikely. We've been definitely way, way conservative, so yeah.
So the sampling rate we've just taken from the ISO standard for couplers. It's pretty well established, and it is based on a statistical, a zero acceptance number sampling plan. So it seems appropriate. Obviously, do what the manufacturer says and put it all together. We're not looking at mistakes in assembly or anything like that. That's not part of this investigation. Although, you know, that does happen. We acknowledge that. But you would be stacking 3 probabilities on top of each other then. We then freeze the test samples, get them a little bit colder than the target, so that when we put them in the test machine, they'll get a little bit warmer. We'll be monitoring that, of course. And then we obviously have to control the speed to what our target is. And this is where the longer specimen starts to come back and bite you. So because your machine has to achieve 10% in one second of that length. So for a 250 mil specimen, that's 25 mils a second. That's reasonable. But if you go longer, obviously that increases. So.
Challenge, yeah.
Yeah, and we're just recording the load, the displacement and strain in the bar, and obviously failure mode of the bar. We're looking at a minimum strength based on 1.15, which is RE, which is yield. So we're really looking to see if there's a brittle fracture problem, which is going to result in much lower strengths than that.
Yeah, we go with the new version of the ISO 1535, which is requiring REH, which is the actual yield strength, not the nominal yield strength as the previous version of ISO 15835, which is still cited by 3101, but yeah, it's less conservative.
And obviously you've got to verify you meet your target strain rate and your minimum elongation over that time. And failure mode and position is pretty obvious, I guess, but ductile yielding of the bar away from the connection. And this text comes directly from 3101, so no thread stripping or distortion.
And so we are proudly introducing the Mjolnir test. That's how we nicknamed that. So Mjolnir is, of course, the name of the hammer of Thor, god of thunder. It's an impact test, so it's cold, Norse mythology. That's fine. Yeah. So
His idea, was it?
yeah, it was mine. And so yeah, and we've actually we started this journey separately, and then we realized that we were traveling towards the same direction, and we joined forces. So what you see here is a couple of tests that with Reid we performed in Australia at Swinburne University. And so I had approval from the company to perform some trials. So what we see here.
Testing in 3, 2, 1.
That's how it looks like. So it's very fast. And yeah. That's what we want to see, a failure of the bar outside of the coupler. Yeah. So this is, of course, still a work in progress. That a lot of things can be refined. The initial test, also this one that you have seen, was quite different before we joined forces. So we changed a lot of the parameters, the temperature, the speed, and the requirements that we had for the strain rate. So it's still a work in progress, but I think it's a good starting point for start testing and proving, if this is an issue, which is apparently something that is not recognized by other international standards, not even 15835 and 15698. But if it's a problem, we need to check if it's a problem or not. So performing the test, I think it's a good thing to do. And yeah, so.
The only thing I was going to say was, we're trying to keep it realistic. Like, we're trying to tie it back to an actual scenario rather than a dreamed up number. So that was the thrust of the work, I guess, is trying to come up with something realistic. So, yeah.
Yeah. So, yeah. Thank you for your attention.